Okay. We got a function f of x equals x to the 2/3, x to the 1/3. The domain is all real numbers, and that's the first thing that you kind of want to consider. It's really the cube root of something squared and the cube root of something. So if the domain is all real numbers, that means then that any value that makes the derivative or the second derivative undefined will be a critical value or a possible inflection value. Now we are on cusp alert, and a lot of people on the test like put cusp alert, but then they never even found the cusps. So the whole purpose of being on a cusp alert is to realize that it's going to be a critical value. The root of each of these, this is x to the 2/3 and x to the 1/3, the value of x that causes both of those terms to be 0 when you plug in for x is 0. So when you're on cusp alert, you're actually on cusp alert at x equals 0. Or it could be a vert alert. It could be a vertical tangent. But x equals 0. He's going to show up as a critical value. And before you even start, it's going to either be like that, it's going to be like that, or it's going to be a vertical tangent that does one of those two. Okay, but you know that something like that's going to be happening at x equals 0. So that's the alert that you need to be on. All right, so let's go ahead and find the first derivative. The first derivative, f prime. We're going to need that to answer question number 1. So it's going to be 4/3 x to the negative 1/3 minus x to the negative 2/3. So that's just a power rule. And I'll show you where you got the checks on the test too. I gave one check for that. Pretty easy. Now to get that into a more useful version of f prime, one that we can easily find zeros of and see where it's undefined, as well as plugging back into to get sign changes, we want it to be a single term. And there's two ways to do that. I'm going to do it both ways. The first way is factoring out least powers, which is the way that I did it in class, the way I encouraged you to do it. You can look for the smaller of the two exponents in this case, which is x to the negative 2/3. You can even factor out a common factor. If you want to factor out the least factor, that's a numeric value, you can factor out a 1/3. You don't have to factor out a 1/3, but I would recommend it. Now notice I'm keeping it equal to f prime. Some people, very few people did this, but you want to make sure you label it as a function. Now you're not just working with an expression, it has a name. So if I factor out a 1/3, x to the negative 2/3. I like the beefy bracket. Now remember, factoring out is the same as dividing out.
Why do you factor out 1/3?
Just because I have a 1 and a 4/3, and I want to get rid of my I don't want fractions in here. Okay? Are you not comfortable with the 1/3? Let's not factor it out then. As I'll show you how it works without it. But I wanted to get rid of my denominator, so I was going to factor it out. But let's say we leave it in there. If it makes it easier for you, now you're just focusing on the x's. That's fine. When you divide out, you're taking what you started with, which is x to the negative 1/3, and you're dividing it by what you're factoring out. So off to the side here, you really have x to the negative 1/3, and you divided or factored out x to the negative 2/3. Now, it's no more difficult than just using your rules of exponents, right? Which says when you're dividing and the bases are the same, what do you do with the exponents? You subtract. So what is negative 1/3 minus negative 2/3? Well, it's really negative 1/3 plus 2/3, which is 1/3. So you get x to the 1/3. Now, before you go on to the next one, check, right? You can always check by redistributing. When you multiply it back in, of course, it's a little bit easier. You know that you add exponents. What's negative 2/3 plus 1/3? Negative 1/3, right where you started. Okay, so you know you factored it out correctly. Now on the next one, of course, you're dividing out the whole thing, so when you divide something by itself, you're left with 1. And it's that easy. Now, the reason it works so nicely is because now you have two factors. The one that's out front has a negative exponent. So you could throw it to the bottom, and it becomes x to the positive 2/3. The 1/3 puts it under a cube root, and I would square it after cubing it rather than squaring it under the radical, simply because that's an easier way to use it, going small before you go big. And the numerator is 4/3 cube root of x minus 1. Now at this point, I'm not comfortable. I'm not liking the 4/3 in the top, so if you didn't factor the 1/3 out in the beginning, now would be the time possibly to multiply by 3/3. So it's just one little extra step, LCM over LCM. And if you distribute, you get 4 cube root of x minus 3 all over 3 cube root of x squared. And that is going to be probably the most useful version right there for our purposes. So I'm going to relabel that as f prime of x. All right, so on the test, I said show that it equals something. And I gave you the answer, and I was actually looking for the work. So some people just did some random stuff and then wrote the answer down, and of course I caught it, right? So you got one check for the derivative and one check for all the algebra involved. All right, now why do we work so hard to get to that point? Because now it's going to be real easy. But before I get to that, let me show you the other way to do it, as I promised. The other way to get to that step is to just rewrite it, each term, without negative exponents. So you have a 4 over 3 cube root of x, which is x to the 1/3, minus 1 over x to the 2/3. And as you remember from a long time ago when you first studied fractions, to combine two fractions you need a common denominator. So it's best to get the least common denominator so that you don't carry around extra baggage. Well, I know I need to multiply this one by 3 over 3 because the first one has a 3. Now the first one has an x to the 1/3. It needs to become an x to the 2/3, so I need to multiply it by another x to the 1/3. And I'm running out of room. Let me bring that out. I need to multiply by x to the 1/3 over x to the 1/3. And that should give me an x to the 2/3 in the bottom, right? So here's what we're left with now. We're left with 4, if you want to call it cube root of x now, all over 3 x to the 1/3 times x to the 1/3 is x to the 2/3. So that'd be the cube root of x squared. Minus 3 all over 3 cube root of x squared. And when you have two terms with the same denominator, you can now add them together and put them all over that common denominator. And notice that you end up with the exact same thing that we have right here. Yes?
Why do you multiply by 3 over 3 over there? Because I feel like I just added more numbers. Like now it's 4 cube root of x minus 3.
Mm-hmm. That's a preferential thing. You don't have to do that. 4/3 is a positive number, and if you're better off in your mind with the ones, that's fine. I just don't like complex fractions, and so it's an option you have.
Yeah, that's what I did.
No, because there's two terms there, right? You can only slide factors from high to low, not terms. Okay, and because this 3, this is really a 1/3 factor in there. The only way to get it is to multiply by the LCM over the LCM, which when you distribute makes that a 3. Yeah. So, yeah, that's an algebraic error, right? Yeah, a over b x plus 1 over c. That is not equal to ax plus 1 over bc. It doesn't work that way because this b is not a factor of both of them. Now, if it were a factor in both of them, it's essentially factoring it out and bringing it to the bottom. Now it would work. So all kinds of little algebraic things that, we've been studying for a long time. I mean, going all the way back to Algebra 2. That's why this problem is so good. That's why it's so important. That's why we're spending a whole extra day on it. Okay? I'm not just going to kind of be content and then keep moving on. Okay, so anyway, whether or not you get the 4/3 in the bottom or top, or the 3 is up to you. If it's a question like I did on the test and I said to show that it equals this, specifically that, then you would have to go ahead and move the 3 to the bottom. But again, that's why I gave it to you on the test. In case you couldn't get to this point algebraically, you could still use the derivative to answer the questions. And when I said people gave up on the problem, that's what I mean. They couldn't get the algebraic version of this, and they just walked away. And there's still a whole lot that you could do once you have this right here. All right, so again, why do we work so hard to get that? Because now it's real easy. And again, watch the notation that I use because that's the notation I'm going to be looking for. And if you don't do this, you're going to lose points. You'll lose points on my exam, you'll lose points on my quiz, you'll lose points on the AP exam. We're going to see where the first derivative is 0 or undefined, and we're going to write it like that. I'm actually going to write that. Now, it's going to be when the numerator is 0 to get the whole thing equal to 0. It's going to be when the denominator is 0 to get undefined. Now, let's focus on the left column first. This is why, by the way, one of the reasons we do that, so we can just set the numerator and denominator equal to 0. I didn't do that. There we go. This is where a lot of people messed up on algebra. So Go through it with me. I need to solve for x on the left. So I'm going to, first of all, add 3 to both sides. Everyone okay with that? I'm going to divide through by 4, and I get 3/4. This step was alarmingly disappointing to me because so many people missed it. We had a different number on the test. We had like the cube root of x equals 1 or -1 or something like that. This is what I saw as an answer, similarly, just like that. That's not really thinking through the problem. That's just kind of like using mathematical reflex to solve it. And you don't want to do that. The whole purpose is to think your way through. Is that how we solve something like that? No. And a lot of people did that. How do you uncube root a number? Cube it. Now, in general, let's look at it from this perspective. Because it doesn't matter what the exponent is. In this case, it's 1/3. You mathematically solve for a base when you have a numeric exponent by raising both sides to the reciprocal power. So if you had x to the 2/3 there, you would raise both sides to the 3/2. You raise both sides to the reciprocal power. And why does that work? Because this rule over here, when you multiply, when you exponentiate two reciprocals together, you get what? 1. And that gives you x to the first, which is x. And now you get 3/4 cubed, which is 27/64. Wow. So there's your critical value. It's a pretty small number. That's where you have a horizontal tangent. Just kind of remembering what we're doing here. We have a nice horizontal tangent right there. Okay, but we're only halfway done with the critical values. By the way, you got to check for that. All right, the next one, a little bit easier. You could just divide through by 3, take the square root of both sides, then cube both sides, but the whole time you're just doing that with 0, and you end up with x equals 0. Okay? Some people at the very beginning on the test wrote cusp alert, but then they never came down here and put x equals 0 as a critical value. And again, that was the whole purpose. We knew of that guy before we started. This is going to be your vertical tangent location. It's going to be one of these 4 things right there. We don't know which one of the 4 yet, but we can do some analysis to determine which of the 4 it is. Okay? So there's your 2 critical values. One where the derivative is undefined, one where the derivative is 0. Both of them are in the domain of the function. Okay, so now whether I ask you to determine the local max or mins, or in this case, determine the intervals of increasing, decreasing, you have to make a number line chart. And you won't get credit on the AP exam for making a number line chart, but on this test, if you made a number line chart, and I could see that you were testing any values with a number line chart that had x and f prime, I gave you a check. So again, if you didn't do that, you gave up on the problem. Don't give up on the problem. Do as much as you can, always. So we got x and f prime, f single prime, and I've got 0 here, and I've got 27/64 right there. Now I got to choose values from the interval. So to the left of 0, like -1, to the right of 27/64, I think 1's going to be great. How do you choose a number that's smaller than 27/64? You either make the numerator smaller or you make the denominator bigger. Either one, okay? Now remember what we're going to be doing with those numbers. We're going to be plugging them in to here. So we're going to be having to take the cube root of the number we choose. So there's 2 options here. If the numerator were a 1, you can't go smaller than a 1. So you're just going to have to make the denominator bigger. But is there a perfect cube smaller than 27? 27 is 3 cubed, right? What's 2 cubed? 8. So maybe I'll choose 8/64. Is that smaller than 27/64? Yeah. Or you leave 27 alone. 64 is 4 cubed. What would be the next number up from 4 cubed? It'd be 5 cubed, which would be 1/25. So either one of those types of numbers would be great to use for testing that interval. Either one of them. Of course, 8/64 simplifies even more to what? 1/8. So I might use that one. Okay, but either one of them would work in either form. I'm going to choose an 8. On the test, I think it was a 1/64 or a 1 something. So you had to choose like a 1/25. 1/125, sorry. Okay, so here we go. We're going to plug them back in to the first derivative, and we're only looking for the SIGN. Now, I heard someone, Sadler, you were saying, I heard you say that the denominator is always positive, right? As you were talking with Marbach a little while ago. I think you said that. I'll give you credit for it. So we don't even have to plug into there, do we? If the bottom is always positive, it's not going to change the sign. Okay? So all we have to do is plug it into the numerator to get the sign. Let's do that. So I get the cube root of -1, which is -1. Times 4 is -4 minus 3 is negative. Okay? There's a negative sign. We plug in a positive 1/8. The cube root of positive 1/8 is positive 1/2. Times 4 is positive 2. 2 minus 3 is negative. So I get another negative there. And then I plug in a positive 1, and I get cube root of 1 is 1. 4 minus 3 is positive 1. I get a positive. So very similar results to the one on the test, where the sign did not change each time. Now, for the intervals of increasing, decreasing, here we go. The function is continuous at 0, remember. The function is continuous at 0. F is decreasing. Notice I put F is. I didn't put just decreasing. I didn't put it is decreasing. F is decreasing. And then we'll list the open intervals. On, now remember, we come back to the critical values, not the test values. So it would be from negative infinity, bless you. Good. You can cruise right through the vertical tangent line because the function's continuous there. We can say it's decreasing through that singularity. Similarly, F is increasing wherever you have a positive sign. On the interval from 27/64, what a wonderful number, to infinity. So that's just testing for intervals of increasing, decreasing. By testing, we mean that we're testing the intervals in between discontinuities, which we didn't have, and any critical values, which we had 2 of. Now, for the first derivative test, okay, let's do the first derivative test. I have a net sign change right there, negative to positive. So F is going to have a what at 27/64? A local min. Some people had a beautiful sentence, but there's still some people who are not writing it this way. And if you're not writing this way, you're probably going to lose points. So if you're content with that, keep up that work. Okay? If not, adopt this script. F has a local minimum, and I'm not going to ask you for the y value. We're just going to say at, okay, not of. At, and then the x value. Well, that's at x equals 27/64. That's a check. Now, here's where some people got an answer. They may have had the wrong conclusion. Okay, the test, I think, had a local max at x equals -1. If someone said that there was a local min at x equals 20 or made up a number, but then the justification was spot on correct based on what they said above, I gave them one of the 2 checks. So don't give up. F has a local minimum at x equals 27/64 since what? F or F prime? F prime. Okay, so here's another common error alert on the test. Several people put F. F measures the y values. This is called the first derivative test. We are looking at signs of the first derivative. It's since F prime changes from negative to positive. Where? In France? No, at that point, at x equals 27/64. Check. You write it like that, you're going to get full credit every time. Okay? So this was worth 2 checks on the test. And again, you could have had the wrong first part. F has a local max at x equals 1,000,000. Since F prime changes from positive to negative at 1,000,000, I'd be like, wow, beautiful justification for a wrong answer. 0, 1. X check. Don't give up. Now, do we have a local max or min at x equals 0? No. Let's see what that sentence would look like, because sometimes you have to discuss every critical value that you come across. So here's what that would look like. F has neither a local max nor a local min at x equals 0, since f prime is negative on either side. And that's the key word, on either side, not of France, but on either side of x equals 0. The word either side implies immediately to the left and immediately to the right. It's a local argument again, okay? Yes?
Well, we have to make that differentiation on each.
Possibly, yeah. But you'll know it because the instructions will say, determine if f has a local max, local min, or neither at each critical value. So when it says at each critical value, determine if it has, and it says neither, that's how you'll know that you have to address every critical value. Sometimes the instructions just say determine the local maximum and local minimum locations, or determine the x values where f has a local max and local min. If they just say that, you don't have to talk about the critical values that aren't. But having said that now, since we know that the function is decreasing through our cusp, we know that it looks like which one of these? It's decreasing through the cusp, so it has to look like the purple one now. Yeah? Right? It's negative on both sides. So our function is decreasing through the vertical tangent.
So while on the quiz, do you have to write that f has neither?
I think I'm going to ask you to do everything that I'm doing today. Yeah, just kind of do the whole package. All right? Increasing, decreasing, determine at every critical value. Yeah. It'll be the same sort of problem. Yeah. All right, now we're not done. The fun is still out there to be had, more fun, because now we're going to be talking about the second derivative. So to get the second derivative, again, you have two options. You can use the Hody-High rule from here. And some people did the Hody-High, and they had their parentheses perfectly intact, and I gave them a point for having the second derivative, even if it was they didn't do anything with it. They didn't give up on the problem. They got the second derivative. Or you could take the second derivative of your first derivative, which, remember, we have another version of it right here. This one is actually a little bit easier to take the derivative of. The other one is already a quotient, so you might have an easier time cleaning it up. Personally, I would probably just take the derivative of the first one because I'm okay with factoring out least powers. So here we go. F double prime would be, taking the derivative from the pink one way up there, we got negative 4/9 x to the negative 1/3 minus 1, which is negative 4/3, minus becomes plus when you multiply by negative 2/3, 2/3 x to the negative 5/3. Okay, on the test, that got a check. If you did the Hody-High minus Heidi-Ho over Ho-Ho, and you walked away, some people, when they did Ho-Ho, didn't put parentheses around their Ho-Ho. When they did Ho squared, you didn't get the check. All right, so never, ever, ever give up on a free response problem. Do as much as you can. Always use the right notation. Make something up, if you're not quite sure, and just go with it, like on these justifications down here. Okay, so now let's go ahead and factor out least powers. I'm only going to factor out least powers this time so you can get used to it. So let's think about the x first. Which is smaller, negative 4/3 or negative 5/3? Negative 5/3. Now, I'm going to go ahead and factor out the fraction too because I don't want to have to multiply by the end. So which one's smaller, 1/9 or 1/3? Those are your denominators. Yeah, the numerators are okay. I have a 1/9 and a 1/3. I'm going to factor out the 9. And then I do have a common factor also of what? In the 4 and 2? A 2. So I have a common factor of 2. So I'm going to factor out a 2/9. Okay? I'm going to show you how to do it. This is a good skill. Remember, factoring out is the same as dividing out. So if you're not sure, go off to the side. What's negative 4/9 divided by 2/9? Well, stay, change, flip. Negative 4/9 times 9/2. Your 9's divide out, and you're left with negative 4/2, which is negative 2. Okay, there's your number. There's your number. Let's do it with the x's now. I got x to the negative 4/3 divided by x to the negative 5/3. The rule says to subtract. Well, it's negative 4/3 minus negative 5/3. I get 1/3 again. That's your x. Okay, I did that off to the side, but I did it where you could see it, so it is off to the side. It's bench work, okay? It's over there. That's legal to do. Now over here, This is funky. I got to factor out a 2/9 from a 2/3. But remember, we're dividing out. We're starting with 2/3, and we're dividing out a 2/9. So 2/3 divided by 2/9, stay, change, flip. Okay, when a dog can do all three of those, he graduates from obedience school. Stay, change, flip. 3. We get a 3. See that? And then the x is gone because we factored it out. All right, so all that little stuff off to the side, we'll just send him over there. He was just to help me, if I can get him over there. All right, there we go. Now notice how quickly this will clean up. I'm going to have a 2 in the top, and then I'm going to have a 3 minus 2 cube root of x, if you want to clean up what's in the brackets. And in the bottom, I have a 9 cube root of x to the 5th power. And I don't have any complex fractions. All right, so there's my simplified, cleaned up version of second derivative. Now we're going to do the same thing. Where's the second derivative equal to 0? Where's the second derivative equal to? dne. All right, well, it's going to be when the numerator is 0 for the whole thing to be 0. So I'll go ahead and carefully set the whole thing in the numerator equal to 0. If I divide through by 2, I'm not going to skip any algebraic steps here. I don't want to make a careless mistake. 0 divided by 2 is 0. If I separate by bringing the cube across, so it becomes positive, I get that. If I divide through by 2, I get 3 halves equals the cube root of x. And one last time, to solve for x now, what do? Do I take the cube root of both sides or cube both sides? I cube both sides. So I get 3 cubed, which is 27, all over 2 cubed, which is 8. So I get 27/8. That is your PIV, your possible inflection value. Now, where's the derivative, second derivative equal to 0 or undefined? It's when the denominator is equal to 0, bless you, which is also going to be when x is 0. There's your other PIV. What do we do with those numbers now to determine intervals of concavity? Do the number line chart. Okay, so here we go. We got x, and we got f double prime, and we got 0, and we got 27/8. Okay, so I'm going to be plugging it back in now to here. This is, again, the second verse to the same song. How about a -1 and a, let's see, something to the right of 27/8? That one's a little different, huh? 27/8. That's about what? 3 point something? So maybe 4. And then what's something between there? Maybe 1 or 2. Yeah. Something that's a nice perfect cube. Maybe 4 is not a good number because we have to take the cube root of it. What's a number that's a perfect cube bigger than 4? 8. How about 8? Yeah. Okay. All right, so now we're plugging it back into the purple, and we're, again, looking at the sign. Now, notice the bottom. The sign of x in the bottom is going to be the sign of the denominator, because when you take the cube root of a negative, you get a negative. When you raise a negative to a fifth, you get a negative. So it's just the sign of x in the bottom that determines the sign. And then the 2 we don't have to worry about. So plugging in a -1, we get the cube root of -1 is -1, times -2 makes it +2. So I get 3 plus 2, which is +5. All over the bottom would be a negative, so positive over negative is negative. Plugging in a 1, I get a 3 minus 2, which is positive, over positive, which is positive. Plugging in an 8, I get the cube root of 8, which is 2, times 2 is 4. So I get 3 minus 4, which is negative, over positive, which is negative. And there you go. So here we go. F is CC up. I'm going to abbreviate CC down first on the interval from -infinity to 0, union 27/8 to infinity. F is CC up on the interval from 0 to 27/8. Do we have any inflection values? Yes. There's a sign change at both, and notice they change for different reasons. So F has an inflection value at x equals 0, since same kind of thing, f double prime changes from negative to positive at x equals 0, and also at x equals 27/8. You can even start a separate sentence since f double prime changes from positive to negative at x equals 27/8. Now the last thing that maybe we can do, we said there was a local minimum at x equals 27/64. 27/64 is between 0 and 27/8, right? So notice that f double prime of 27/64, which is our critical value. Notice what was the concavity there? It's this middle interval. It's positive, greater than 0. Positive means concave up, so you could use the second derivative test. So f has a local min at x equals 27/64. And that's the second derivative test for local extrema. When you check for intervals of concavity, you don't do the inequality. A lot of people in the test, I just asked for concavity, did the second derivative test. I'm going to record this. I'm going to put it into the shared folder, not on YouTube. If you need to go through it again, quiz will count as a double grade tomorrow on this stuff here. Have a good day.